To summarize, we now know that we can convert alkenes into ketones and carboxylic acids, either with the reaction of potassium permanganate at room temperature or higher temperatures, or with the reaction with osmium tetroxide and periodic acid as oxidizing agent. And the conversion of the carbon-carbon double bond into the carbon-oxygen bond is an oxidation reaction, and such an oxidation reaction can also take place if we use ozone. And for this reaction, we will now have a closer look on what is going on there. So first of all, we need to understand what is ozone. Ozone can be found here. It is a molecule with 3 oxygen atoms, and there is a positive charge on one oxygen atom and a negative on another, and therefore this molecule is dipolar. And then you can imagine that the negative charge must not be necessarily on exactly this oxygen atom, but you can also have the negative charge on this oxygen atom. That means this molecule has resonance forms. And ozone is also called a 1,3 dipole. So what happens now if we have the reaction between an alkene and ozone? We have again a concerted reaction step. That means the carbon-carbon double bond will give the electron pair towards this oxygen atom. Then at the same time, the electron pair of this oxygen-oxygen double bond will move towards the positively charged oxygen, and then the negatively charged oxygen will give an electron pair towards this carbon atom in order to form a new oxygen-carbon bond. And all these steps happen at the same time. So we have again a concerted cycloaddition reaction. And the cycloaddition reaction proceeds over a cyclic transition state where we have a 5-membered ring, and the 6 electrons are delocalized over this 5-membered ring. This transition state consists out of these 5 elements, so the carbon here, the carbon there, oxygen, oxygen, and next oxygen. And as the 2 oxygen atoms of the ozone, which are involved in the new formed carbon-oxygen bonds, so this one and that one, have a 1,3 relationship, and ozone is a 1,3 dipolar molecule. This reaction is called 1,3 dipolar cycloaddition. After the 1,3 dipolar cycloaddition, we end up with this molecule, which contains a 5-membered ring. And this molecule is called molosonite. And molosonite is very unstable because it contains 2 very weak oxygen-oxygen bonds. And hence, a reverse 1,3 dipolar cycloaddition will follow immediately. And this reverse 1,3 dipolar cycloaddition starts with the movement of one electron pair from an oxygen atom towards carbon. So you can see this first step here, and the electron pair from the oxygen will go here in order to form a new carbon-oxygen double bond. At the same time, the carbon-carbon bond will break, and the electron pair will go up towards this oxygen atom. And then this oxygen-oxygen bond will break, and the electron pair will go towards this oxygen atom. So this is quite similar to the first step, but the other way around. And after this reverse 1,3 dipolar cycloaddition, we have then broken one oxygen-oxygen bond and one carbon-carbon bond in order to form one carbon-oxygen double bond and a carbonyl oxide, which is also a 1,3 dipole. And if you now watch at this carbonyl oxide, you can see it looks quite similar to our starting material, the ozone. So again, we have positive charge and a negative charge at the oxygen atoms. And this other molecule is now aldehyde. Then we have another step, and in this step, the carbonyl oxide will react with the carbon-oxygen bond of the aldehyde in a second 1,3 dipolar cycloaddition reaction in order to form an ozonide. However, this reaction can only proceed if the aldehyde flips so that the negatively charged oxygen of the carbonyl oxide can easily attack the partially positive charged carbon in the carbonyl bond. You can see this here. We have to flip aldehyde so that here this partially positively charged carbon atom is more or less easy to reach for this negatively charged oxygen. And then the reaction is in a 1,3 dipolar cycloaddition. That means we have a concerted reaction where all electron pairs move at the same time. So we have the attack of this negatively charged oxygen. The electron pair moves towards this carbon atom. At the same time, one electron pair from this carbon-oxygen double bond will move towards the other carbon atom. And then this electron pair of this carbon-oxygen bond will move towards the positively charged oxygen. And afterwards, we have this final product, which is the ozonide. And now important is that ozonide is formed as a mixture of diastereomers because the 5-membered ring is formed with the R groups on the same or opposite side of the ring. What do we now know? We have the formation of ozonides realized via 1,3 dipolar cycloaddition reactions, and now we have an ozonide. And ozonides are already much more stable compared to molosonites, but they are still very reactive, and usually they cannot be isolated from reactions and they even explode. So, what is now our next step? As ozonides are so reactive, they are usually converted into more stable carbonyl compounds by reacting either with reducing or oxidizing agents. And depending on the reaction conditions, so if we either use reducing conditions or oxidizing conditions, then the products will look different. If we use reducing conditions, the ozonides will be transformed into aldehydes and or ketones. Conversely, if we use oxidizing conditions, then we will end up with carboxylic acids and or ketones. And the overall reaction of alkenes with ozone in order to transform the carbon-carbon double bond into 2 carbonyl compounds, followed by the reaction with either reducing or oxidizing agent, is called ozonolysis. And to sum it up, if the alkene reacts with ozone, the second step determines the final products. If we have a second step with reducing conditions, then we will get ketones and aldehydes. Conversely, if we use oxidizing conditions for the second step, we will end up with ketones and carboxylic acids. And now what is also important is that we see that the final products can then, of course, vary depending on the R substituents. And important to have in mind is also that the ketone and the aldehyde can also result from the reaction of the alkene with osmium tetroxide and then in the second step with the reaction with periodic acid. So you can have several ways how to get the ketone and the aldehyde. Finally, I would like to summarize all possible oxidation reactions of alkenes. So, first of all, we have the reaction of an alkene with peroxycarboxylic acid, which results then in an epoxide. Then these epoxides can further react in so-called ring opening reactions, which are either acid or base catalyzed, and hereby we form anti-1,2 diols. Conversely, if the epoxides react with osmium tetroxide, then we will form selectively syn 1,2 diols. And we get also the same products, so also syn 1,2 diols, if we use not osmium tetroxide, but instead potassium permanganate in a cold reaction medium. Conversely, if we have not a cold reaction medium, but a temperature which is around room temperature or even warmer, then we will produce ketones and carboxylic acids. And if the alkene reacts first with osmium tetroxide and afterwards we use periodic acid as oxidizing agent, then we will produce ketones and aldehydes. Then we still have some other possibilities. We can use ozone and oxidizing conditions in order to produce ketones and carboxylic acids out of alkenes, or we use ozone and reducing conditions, then we produce ketones and aldehydes.